Alright, so in this training we're going over dryer, push to start switches, and motor operation. It's going to be a real quick overview of it and just kind of running through how they work. I was just on Reddit and saw a post of someone saying their motor wasn't starting, wasn't kicking to life, their push to start switch had a continuity and fuses were good and what have you. So it prompted me to make a quick training kind of on how the basic operations work. So in this, we're going to go over some basic electricity. We're going to go over push to start switch, motor circuits, and some basic diagnostics. On this one, it's an NGD 4655, but when it comes down to motor operations in dryers, regardless of whether it's a gas dryer or an electric dryer, the motor circuits are pretty much exactly the same. So that being said, let's take a quick look at the motor circuit. Pretty simple, but the motor itself needs 120 volts AC to operate. If it's missing either line or neutral, it's not going to kick to life. Now, with that being said, pretty much with any appliance, you're going to have switches, and they're going to be used to either open or close the line or the neutral circuit, and in this case, to the motor. So without both present, both line and neutral, to the motor, our motor's not going to operate, plain and simple. Right here, you can just see this is where the motor connections are. Not really going to dive too deep into that, but with that being said, let's jump into it. So to see how a motor gets both line and neutral, we would want to refer to the wiring diagram or the schematic, and we would use this to find our load, in this case the motor, which is right here, and we would also use it to see what stands in the way of that load or the motor from getting line and neutral. One thing you hear me say throughout all the training that I provide, you want to reduce the problem. And when I say that, when I say reduce the problem, when you're looking at a diagram, something like this, you got all this going on here and this kind of covering it up, got a lot of other stuff going on there, and that can be kind of overwhelming, especially if you're new to reading wiring diagrams. So the easiest way, for me at least, that I've found is to reduce the problem. And what I mean by that is all we care about in this instance is our motor circuit. So therefore, the heating circuit down here, we don't care about that. I don't care about that thermal fuse. It has nothing to do with the motor. So reduce the problem. And when we reduce the problem, we can see here's our motor. And what we want to do is see how it gets line and neutral. So up here on this side, we've got L1. L1 comes down, comes into the timer, branches off, and comes down here. So this is going to be one switch right here that could be preventing our motor from getting voltage. And you can see it's C to B needs to be closed. So C to B, those are going to be contacts inside the timer itself. So assuming you set the timer to, let's say, a time dry setting, inside it's going to close this contact and supply line voltage down here, and it's going to branch off. And again, we're not worried about what's going on over here because that doesn't have anything to do with the motor circuit. If our motor isn't kicking on, I don't care about the heating circuit. I don't care if line voltage is coming down over there. I care about whether our motor's getting that voltage. We're reducing the problem. So in a working circuit, you have it set to say time dry. This contact should be closed, and we can see line voltage comes right on down. Now the one thing about this circuit, taking a look at it, there's no thermal fuse in here. A lot of times you're going to see a thermal fuse between the motor and that for line. So that's one of the other good reasons as to looking at diagrams and schematics. I know there's no thermal fuse here. So in that Reddit post where the person was saying they were checking the fuses, like I'm looking at this diagram, there's no fuses here. So, there's no need to check the fuses. You can if you want to. It doesn't hurt while you're there. If you're a professional appliance technician and you have access to a fuse, it doesn't hurt to check it. But with that being said, there's no fuses on this circuit per here. So, in a way it's a waste of time, but not really. Nonetheless, so being diligent, we're tracing down the voltage, comes up to here. This is how our motor gets line voltage. Now let's take a look at the neutral side. Neutral comes in, it comes over here. First stop is the door switch, right there. If the door switch is engaged, if it's shut, if the contacts are closed, neutral comes up, down through here, kind of branches off. This is sort of relevant, but we're going to get into that in a little bit. But for the intents of what we're learning right here, neutral comes up, and then the next stop is the start switch, or this is going to be the push to start switch. So that's pretty much our motor circuit. So in order for our motor to work, there are 3 different switches that need to be closed in order for our motor to get line and neutral. Plain and simple. We looking at the diagram, we can reduce the problem to one of 3 things, or one of 3 switches if we're missing voltage somewhere. We've got this switch inside the timer, we've got this push to start switch, and you've got this. Now, of course, that's not saying the motor's not bad. It could be the motor's getting 120 volts and not doing anything, or it could be a wiring issue. But this is just basic training. We're not really deep diving into it too much here. So the main point of this slide is, hey, just take the time. Figure out what switches are in the circuit. Where could our failure points be? And then we can start figuring out where we're missing voltage. So in the standby mode, in this previous slide, that was just kind of showing how the motor is getting line and neutral. Of course, with blue being neutral, 0 volts, line being that, we wouldn't actually have it configured in this way because that switch is open. But it's more for, just visual purpose. Now, if we're talking more legitimately or more realistically, if the motor circuit's in standby mode, let's say you have it turned to time dry, but you don't have the push to start switch pushed down yet. This is kind of where we would expect to see our line voltage. Line voltage would be coming down through the timer. The timer is going to be kicking it over this way, and it's going to come down to the motor. Now, this is one of those concepts that I like to impress upon you because, this is kind of how circuits work. Now, whether or not I'm getting the terminology spot on, that's up for debate, but point aside, line voltage is coming through. Since we do not have neutral up to the motor, line voltage passes through the motor, and it comes up here. So without neutral supplied to the circuit, line voltage is backfeeding up to the push to start switch. Right there. So, in theory, if you go to the push to start switch, you have it set to time dry, let's say. If you check AC voltage across that without it being pushed down, you should read 120 volts. That would indicate you've got a good circuit. Now, I always like to check with live voltage. It's always been more it makes more confirmation, I guess, live voltage rather than disconnecting a whole bunch of stuff, doing continuity checks. So with that being said, let's just say I'm right over here. I have 0 volts if I check there, although I'm expecting 120. If I check this line to chassis ground and I have 0 volts, guess what my next check's going to be? I'm going to come over to the timer wire, this light blue wire that comes out of the B contact. I'm going to check that to ground. If I have 120 volts to chassis ground from here, 0 volts to there, then guess what? We either have a bad motor, a loose connection, or a broken wire. Because we have voltage here, but not there when we're checking to ground. That means our 120 volts it's not making it there. It's there, but not there. You kind of get the point? That's why I like live voltage. Now, with that being said, let's go on to the next slide. And let's talk about the push to start switch for a moment. So with the push to start switch on this style, it's a momentary switch. It's just spring loaded. You push it down, and when you release it, it comes right back up. So when it's engaged, it closes the electrical circuit, and it supplies neutral down to the circuit. It'll push neutral through over there. So in the open position, you're going to kind of see something like this. Let's say this side is over here. We've got line voltage, should have 120 volts there, 0 volts there because the contact is open. So in this circuit right here, if you were seeing this, if this was a good working circuit, if you put one lead there with the connectors on, you would read 120 volts. And you can kind of see what's going on there. Line voltage back feeding through the motor up to this side of the push to start switch. Neutral is coming down through here, over here, and it's sitting on this side, just like what you see there. Pretty simple, right? There's no need to overcomplicate some of these things. The main thing is just understanding what you're seeing when you're reading your meter readings. And this is why I like doing these trainings, kind of reiterating the same thing over and over. And if you've watched enough of the videos or enough of the training content, it can kind of seem like I'm beating a dead horse. But I see so many techs on a day-to-day basis not understanding the concept of voltage and voltage potential. And that's really a strong diagnostic tool to have. So with that being said, when the switch is pushed down, when the user presses that start button, it closes those contacts. You can kind of see there, that switch is shut. We have a complete circuit. So in a working circuit, as you can see here, neutral is now pushed through to the motor, and the voltage is being dropped across the motor. We no longer have 120 volts there. We'd have 0 volts. So let's go on and move on and talk about the motor centrifugal switch. Basically, you got your standard motor right here, and then this right here is the centrifugal switch. It's actually built in to the motor right back on this side, but we got a nice picture here, and it can kind of show you what this looks like. You're going to have this plastic disc, and what happens is when the motor kicks to life, it starts spinning really fast. This switch pulls in, and you can kind of see how that'll work. When that pushes in, it closes that. Those become straight like that, and it closes some electrical contacts over here. So the switch, the centrifugal switch, it actually serves multiple purposes. For one, it will close the heater circuit. So the heater circuit will only kick on if the motor is running, in theory, unless you've got like a grounded element and we've got voltage going to it. But in theory, the heating element or the heating source should not kick on if the motor is not on, because part of the line voltage or neutral comes through here, through the centrifugal switch, and then back out. Now, this training is not really on the heating circuit, but I just wanted to throw that out there. Now, on this unit in particular, the centrifugal switch, it also redirects neutral, and we're going to dive into that in a minute. And then pretty much it's just a safety device. So if the motor's not running, we don't want any heat to the unit, things like that. So let's go ahead and take a look at it, the centrifugal switch, and applying what we just learned to the motor when it's actually running. So the user pushes the push to start switch, neutral feeds back over here, voltage is dropped. When the centrifugal switch engages, we can see right here, look at that, neutral takes out the start winding. It removes the start winding from the motor. The start winding's there for that initial torque. It gets a lot of extra power. Once that power is achieved and the unit's running, it takes the start winding out of the circuit. Not only does it do that, it then redirects neutral through this line. And you can see this circumvents the push to start switch. So when you push it, you get that initial startup torque, and then boom, centrifugal switch there. You can release that, and guess what? Our motor still has line and neutral. And this is pretty much how the motor will keep running even though the momentary push to start switch is open. So when you have a motor or one of these dryers with this configuration in particular, where you push it down, the motor starts and it runs, and then you release it and the motor stops, that's a pretty good indication your centrifugal switch has failed. We're not getting that contact to connect neutral. And again, as you can see, neutral comes in, bypasses that push to start switch, comes over, and there you go. Remember, a load needs line and neutral to operate. So, and again, I kind of went over this before, but the motor circuit is pretty much the same, whether you're dealing with gas or electric. The only difference on gas versus electric is the heating circuit. So, with that being said, let's go ahead and talk about voltage potential. Voltage potential is the potential difference between 2 points. So, if you take your standard 120 volt outlet, what that is, when you're reading 120 volts on your meter, you're reading the voltage potential difference between 120 volts, which is line, and 0 volts, which is neutral. Neutral is a known 0 volt source. So in this instance, we got our meter leads, one right there, we're reading 120 volts. Now what I mean by voltage potential, let's just say you take this black lead and we would put it right there. Do you think we would read 120 volts, even if we had 120 volts there? No, we'd read 0 volts. If you put both of these leads right here on this 120 volt line, you would read 0 volts. Why is that? Because there's no voltage potential difference between where these two leads are. When you're checking voltage, it's always with reference or in regard to another test point. This right here is a known 0 volt source. This is a 120 volt source. 120 plus 0 is 120. And that's pretty much the basic of voltage potential. And I always like using that because, continuity, it can trip you up. But anyways, in a working unit at the push to start switch not engaged, you should see 120 volts. That's if the timer is set to, say, time dry. Line voltage is passing up through the motor, and it's coming all the way up to this side of the push to start switch. So when we shut the push to start switch, when you press it shut, that 120 should drop to 0 volts. There's no voltage on this. And neutral's pretty much pushing back through to this side of the motor. And now the motor's kicking to life. You can see the centrifugal switch there, and now it's connected neutral up through there. Our voltage is pretty much just being dropped across the motor. Now, let's just say, and this is a test I use all the time on these units, quickest, easiest way to do it. You don't have to unplug stuff, check continuity, plug it back in, figure it out. You just take the back panel off, you put your leads there on live voltage. And I've had this happen many times. Dryer won't start. Push to start switch, you can maybe hear a click. Okay. So I put my leads across it, I push down, or I should say I put the leads across it, and in its normal state, set to time dry, I'm getting 120 volts. When I push the push to start switch down and I still see 120 volts, guess what? We've got a bad push to start switch. It's not closing neutral to the circuit. One way you can kind of prove that out, if you just put a jumper wire between those two. I would, of course, recommend unplugging the unit first so you don't get a little spark, but that's definitely one way you can do it. And then when it comes down to voltage potential, that same concept applies to any switch. So let's say the door switch has failed and the push to start switch is pressed. Well, guess what? Line voltage is going to pass through that push to start switch. It's going to come all the way back up here to the motor. Or not to the motor, sorry, the door switch. So if the door switch, let's just say the contact in there is completely broken. It's fried. Well, neutral's coming up on this side, but we have nothing to connect that. So line voltage is feeding up here. You'd read 120 volts across it. And of course, you can put a jumper wire there as well. But, yeah. So let's see here. You would see 120 volts across the door switch wires if it's broken and you're pushing that down. If you release it, it would go back to 0. So one other thing I kind of wanted to throw out on these, because the timer dryer models are very easy to work on once you get the hang of them. But if you're new to them or if you're not familiar with wire diagrams, they can be a little disconcerting. That being said, one final thing I kind of wanted to toss in here. When it comes down to timer contacts on here, we know line voltage comes in right to this C contact as it's labeled right there. Now, if we take a look at this diagram, which is going to be on that wiring diagram, we can see the C contact right here, which is a black wire. So we know line voltage comes into the timer right there, and it's the same layout. This is pretty much a pictorial drawing, same thing. It's not wiring diagram where it's all over the place. If you look at the back of the timer, you're going to see all these same connections, T2, S, F, T, X, H, so on and so forth. So line voltage comes into C, and then for our motor circuit, B, this light blue wire, goes to the motor circuit. So we know within the timer, line voltage is coming from C to B, right there, C to B. And again, you can check AC voltage across this. If you set it to a time dry setting, you don't even have to hit start, the push to start button. If you rotate the timer to a time dry setting, as you can see in the diagram, if we come back, let's see here, to here, if that's closed, it's supplying line voltage to it. We don't need any other position or setting or anything like that. Let's see here, there we go. So if you have it set to time dry setting and you're getting 120 volts from C to B, you think it's a bad timer? If you do, then you're on the right track. And one thing you can do, as I keep saying, you can put a jumper wire there. Now, if you're getting 0 volts from C to B, let's say you're checking C to B and you get 0 volts. Do we have a bad timer? Well, we don't know yet. I mean, more likely than not, it's good, but you need to do another check. What I would do, C to chassis ground. If you're getting 120 volts, check your B to chassis ground. If you're getting 120 volts, guess what? This contact right here is closed. If you're getting 0 volts here to ground, 0 volts here to ground, then guess what? We're missing line voltage coming to the timer. Plain and simple. Really, when it comes down to appliance repair and any electrical related issue, it's a matter of checking where your voltage is and where it isn't. So when you're dealing with a load that won't kick on, and it's going to be a motor in this instance, you need to determine what it needs to work. And in this case, it's 120 volts. And then from there, you can zero in on what would prevent it from receiving, either a or, line or neutral. For us, the schematics or the wiring diagrams, we use those to figure out what switches might prevent either line or neutral from getting the load. And I just realized a spelling error there. Use the schematics, not us, the schematics. And you can use the concept of voltage potential to make live voltage checks to zero in on where the failure is.